I would like to discuss a unusual situation where the wave amplitude grows with time. Any wave, electromagnetic or electrostatic, when propagates through a medium, and if its amplitude grows with time, then we call this wave as an unstable wave, and this entire phenomenon is called instability. The easiest way to excite a wave is by using an electron beam, and so in the plasma there will be two kinds of particles: the plasma electrons, which are not having initially a drift velocity, and there is another stream of electrons which is launched from outside, which is moving with initial finite velocity, finite drift velocity. So, we call them as two streams of electrons, a stationary stream and a moving stream, and hence this instability is called true stream instability. The system in which you have a beam and a plasma is called a beam plasma system. I would like to begin today by describing a simple beam plasma system. Then in such a system, what is the physical mechanism of growth of a wave? We shall discuss that. Then when we begin the solution of Maxwell's the equation of motion and equation of continuity, we have to start with an equilibrium. So, we shall describe an equilibrium and then use the perturbation theory to obtain plasma response and beam response to an electrostatic wave. We will deduce a dispersion relation and obtain the growth rate, and if time permits I will discuss the saturation of instability. Presentation is based on two books, Introduction to Plasma Physics by F. Chen and The Theory of Plasma Waves by T. H. Sticks, but you can find this treatment in any book in plasma physics. This is a very common problem in plasma physics. Now, consider a beam plasma system, a simplest beam plasma system. Normally, you have a tube, plasma tube, which is a vacuum chamber. Long vacuum chamber may be more than a meter long, and there may be a pump here to create a vacuum. Obviously, you create a vacuum of the order of 10 to minus 4 torr, and 1 torr is 1 millimeter of mercury pressure. And here you have to launch an electron beam. So, this is a gas at low pressure, and then you have a very special kind of gun which has two rods to which a tungsten filament is tied, and then you have a outer cover, a cylinder which has a hole here. The potential difference between these two rods of the order of 9 volts is given. So, I will put a battery of 9 volt here, between these two, and this hole, this outer cover is treated as an anode. It is normally grounded, but a potential difference between these two, a huge potential difference between these two is given. So, what happens that this small battery heats the electrons in the tungsten filament, the electrons come out from here, they are pulled by the electric field in this gap region, which is applied a potential difference of V 0, then the electrons come out here and they form a beam. When the beam travels through a gas, it ionizes the gas and creates a plasma. So, typically it will produce a plasma in this region. The gas is ionized outside, but in the inner region this is, so this is a plasma. So, you have created a beam plasma system. In this region there are electrons of the beam, there are electrons of the plasma, and there are ions. This is goes to the pump. In order to have a better confinement of the beam so that it does not diverge, normally many systems have a magnetic field here. By using a coil here, this is the schematic of a magnetic field coil. So, bypassing means this is actually a solenoidal turn that is wrapped over this chamber, and by passing a current in that you will produce a magnetic field in this direction. But magnetic field is not necessary for the growth of instabilities. In fact, in the presence of magnetic field, different kinds of plasma modes exist and a new kind of instabilities appear. But even if this magnetic field is not there, you will have the true stream instability, the basic instability, the growth of plasma wave by the electron beam. This is the simplest schematic. The beam velocity is controlled by the beam voltage, the voltage of this gun. This entire thing is called electron gun or a diode, and the beam velocity you can easily say that half mv square of beam velocity is equal to twice E v0 upon m under the root, where E is the magnitude of electron charge, m is the electron mass, rest mass, and this is the velocity that you will get there. Usually such beams have only milliampere current. If you want a large current, and one can produce beams which can carry currents in several amperes or even kiloamperes, then you require to design a different kind of beam. One possible configuration is called field emission diode. A field emission diode is something like this. You do not have to heat the cathode. A field emission diode has a plate here and a hole here. On this cathode plate you have a knife edge, circular knife edge, very thin knife edge. I have drawn these two lines here, but this essentially is a ring. So, this is a circular ring of this much diameter, being a knife edge, and the distance between these two, this is a cathode and this is anode. The potential difference between these two, if you give of the order of 1,000,000 volt, and the separation you keep here of the range of the order of about a few millimeter, then the even if this is cold, due to field emission, electrons are emitted from here, from these knife edges, and they will get out here. They will give you what we call as the hollow electron beam. So, the electrons will be coming out here. Actually, you can have a circular hole here. So, they will come out here, electron here and electron there, and this is a circular symmetry. So, this is we call the hollow electron beam. And this is what we call as the field emission diode. This is cathode, this is anode, this is field emission diode. And it is used in free electron laser. Free electron laser is a very powerful device to produce coherent radiation, coherent electromagnetic waves over a wide range of frequencies, and the frequency of radiation can be controlled by the beam energy, which is controlled by the beam voltage, the voltage that you apply here. So, this becomes a tuning parameter. You can this brings in tunability of the frequency of radiation. Anyway, today I would like to discuss the physics of how an electron beam can generate a electrostatic wave. In one of the next lectures, I will then discuss how an electron beam can generate an electromagnetic wave. And a travelling wave tube or Cherenkov free electron laser, normally we have an electron beam that produces an electromagnetic radiation. So, these two issues I am going to address in these lectures. So, let me begin with a simple problem of generation of a wave by an electron beam. But before I venture into that analysis, instability analysis, I would like to discuss the physics, but before that a word about equilibrium. What I am considering some sort of a plasma, and suppose this is a region of plasma in which an electron beam is launched. What will happen? Initially, when the beam was not there, the plasma has, suppose a preformed plasma, it has equal number of electrons and ions, so that there is no space charge anywhere. But when the beam goes in certain regions, suppose this is the region where the beam goes, so temporarily there is an excess electrons because additional electrons have arrived here, so there is a net space charge. That net space charge will do what? It will repel the electrons of this region radially outward. The beam electrons will also be repelled, but they already have a large velocity in this direction. So, they will not move much in the transverse direction during their passage, but the background electrons will move. So, a steady state will be realized pretty soon when the net space charge in this region is not there, additional space charge moves to the edges outside. So, in the region of interaction, this is called the region of interaction, I can still presume space charge neutrality, means the density of beam electrons, initial density of beam electrons, initial density of plasma electrons is equal to initial density of ions in the system. This is the equilibrium that you will obtain. So, my issue now is I do not want to consider the effect of finite transverse size. I will consider the propagation of a large cross section beam through a large plasma, ignoring any boundary effects, how the beam gives rise to the growth of amplitude of this a plasma wave in the system. This is the issue. Now, physically what do you expect? If a beam has to generate a wave, it should have three properties. First property is that the beam should be slowed down by the wave. Beam must be slowed down by the wave. How can it slow down the wave? If my beam is going in this direction, for instance z direction, this is the beam velocity, equilibrium velocity in the z direction, then the wave electric field must also be in the same direction, so that this velocity, this beam is slowed down, means E must have a component in the direction of beam velocity. This is one should not be 0, this is very important condition. Second condition is that the frequency of the wave as seen by the beam should be small. We have seen that the response of electrons to any electrostatic field is inversely proportional to frequency. So, what you require is that the frequency of the wave as seen by the beam should be nearly 0. If the wave is of frequency omega and k is the wave number, then the Doppler shifted frequency is omega minus k dot beam velocity. This should be nearly 0, because we know that response of electrons, the drift velocity electrons acquire due to a wave or density perturbation that they acquire is inversely proportional to frequency. Smaller the frequency, larger the response. So, the effective frequency, this is the effective frequency of the wave as seen by a moving electron, this should be nearly 0. This condition is also known as Cherenkov resonance condition. Cherenkov resonance. This is a very important condition. And third thing, any electrostatic wave has electric field in one direction in some region and the electric field in the opposite direction in some region. So, physically you would expect that if I launch a wave and a beam together, then somewhere the beam will be retarded by the wave and somewhere this will be accelerated by the wave. So, net energy transfer is possible when the more electrons are retarded by the wave, so that they give energy to the wave. So, there should be net bunching of electrons in the retarding zones. Bunching of the beam, beam electrons. These three conditions must be satisfied. Well, with an electrostatic wave this is possible, because if I launch an electrostatic wave in the direction of a beam, then the wave has a longitudinal component, so this condition is satisfied. This is also possible because phase velocity of a plasma wave could be less than beam velocity or comparable to beam velocity, so this condition can be satisfied. And we have to see how bunching is possible. This physically I would like to explain before I venture into the mathematical analysis. So, let me explain this mechanism of electron bunching. I think this is the crux of true stream instability. But I am considering a wave, electrostatic wave with electric field Ez is some amplitude A, say cos omega t minus kz. This wave has a frequency omega and is travelling in the direction of z with phase velocity omega by k. I would like to understand the effect of this wave on an electron beam which is moving with velocity v0b in the z direction. In order to understand this interaction between electron beam and the wave, go to a frame of reference moving with velocity of the wave. Moving with velocity of value omega by k magnitude and in the z direction. So, if you go to a frame of reference moving with this velocity, in that frame the frequency of the wave, Doppler shifted frequency of the wave will be 0. So, in this frame the electric field will be like this. So, let me write down the electric field of the wave in this frame. So, in the moving frame you get Ez is equal to A cos kz prime. Z prime is the coordinate, z coordinate in the moving frame. Now please plot this as a function of z prime. If I plot Ez as a function of z prime, what do I get? This is a cos function, it will have this sort of variation. Please remember, this is the region where Ez is negative. So, this is the electric field in the backward direction, and because the electron has a negative charge, so this is called the accelerating zone. This is called the retarding zone because the electric field is positive in the forward direction. So, here I can call this as retarding zone, because if the electrons are going in the forward direction, the force on them will be in the backward direction, so they will be retarded. And this is the region called accelerating zone. This is accelerating zone. This is also accelerating zone here. So, there are alternate zones where electrons are retarded and accelerated. I want to understand the interaction of an electron beam with such a wave. In the plasma, electrons are all everywhere and the wave also exists everywhere. So, suppose those electrons are there, these are the electrons I am locating, and so on. These are the electrons that I have located, indicated. There are three possibilities that these electrons are travelling with the same velocity as the wave. So, one case when beam velocity is equal to omega by k V0b, the equilibrium beam velocity is equal to phase velocity of the wave. What happens in this case? In the moving frame, the electrons will look like stationary. So, in this region the electric field is positive and in this region the electric field is negative. So, what happens? Electrons here would like to move in the backward direction and here the electrons will like to move in the forward direction. So, this is the boundary. Actually, what happens? The electrons here, they are experiencing a forward force. So, if you look at any boundary, the number of electrons crossing the boundary will be same. Let us see how. The electrons which are here, they will be going from here to here because the force is opposite direction. The ones which are here, they will go in this direction. So, the net transfer of electrons from one area to another area will be 0, and hence there is no net increase in the number of electrons in the retarding zones or accelerating zones. So, roughly half the electrons are retarded by the wave, half the electrons will be accelerated by the wave, and there is no energy transfer. For the growth of the wave, you require more electrons should be retarded so that their energy goes into the wave. So, no energy transfer because same number of electrons go from retarding zone to accelerating zone as go from accelerating zone to retarding zone. So, no growth of the wave. Second possibility is that the beam velocity is slightly bigger than omega by k. In this case, what will happen? If you plot the same graph Ez as a function of z prime, the variation is like this. these are our zones, retarding zones, accelerating zones alternately. So, this is my retarding zone and this is my accelerating zone. This is my accelerating zone, this is my retarding zone and accelerating zone, etc. Now, here the electrons are moving slightly faster than the wave. So, in the moving frame they will look like moving. When the wave is not there, they start looking like moving in the new frame. Now, the electrons which are in the accelerating zone, they are accelerated further. So, they will quickly move from the accelerating zone to retarding zone, whereas the ones which are in the retarding zone, they are retarded. So, they will spend more time in the retarding zone and will take long time to get out from there. As a result, there is a reduction of electrons in the accelerating zone and a bunching of electrons or increase in their number in the retarding zones. So, in this case, electrons spend more time in retarding zones, hence bunch over there. This is an important thing. So, when more electrons are getting retarded in the retarding zones, there is a net transfer of energy from the electrons to the beam and wave grows. So, this is the basic physics of energy transfer from electrons to the wave, that their velocity should be slightly more than the phase velocity of the wave, only then this phenomenon is possible. So, physically we have seen that the condition for energy transfer from particles to wave is that the beam velocity should be more than the phase velocity of the wave. Now, let us carry out a mathematical analysis. I think before I take up a mathematical analysis, it will be very useful to look at the energy and momentum conservation in this process, because one can view the generation of wave as a quantum process. So, quantum mechanically suppose the electron beam initial energy is is equal to half m v0 b square. Initial momentum you can easily write is equal to m v0 b, and suppose in the z direction. After this electron has emitted or generated a photon, so after emitting the photon or phonon, plasmon, whatever you call, of energy h cross omega and momentum h cross k, electron energy is final energy is half m v0 square minus h cross omega, and final momentum is equal to initial momentum m v0 bz minus h cross k. But kinetic energy and momentum are related to each other, and the relation is energy is equal to momentum square upon 2m, where m is the mass of the electron. Just substitute it here and recognize that usually the value of h cross omega is less than an electron volt, whereas the value of this quantity is much bigger. If you are launching an electron beam of 200 electron volt energy, then this quantity is 200 as compared to this. This is even bigger. So, you can ignore, when you square this momentum square, you can ignore the higher powers of this and just substitute this there, and it turns out to be omega should be equal to k V0 b, and if there were a angle between the two, between k vector and velocity of the electron, then there is a dot product here. So, this is a Cherenkov resonance condition, the same condition which we say that the Doppler shifted frequency of the wave as seen by the electron should be nearly 0, the same condition. So, this is another way of looking at the generation process, that if the electron has to really generate a wave in a resonant fashion, the wave frequency that it want to generate and the beam velocity should have this relationship. So, this has a quantum mechanical interpretation also. Now, let us carry out the instability analysis, which is rather simple. What we have to do? We have to begin with an equilibrium and solve the equation of motion. What is our equilibrium? First of all, I will write on the beam equilibrium. The beam has a density n0 b in equilibrium. It is a drift velocity, I will call this as V0 b and is in the z direction. The beam has no temperature, no collisions. Let us understand the problem in a very simple way. And plasma electrons what do they have? Their density suppose is n0 and their drift velocity is 0, they are not moving. I will ignore the temperature term also for the time being, and later on we will generalize that what is the consequence of electron temperature. So, simple problem. And then I want to say that suppose my system has an electrostatic wave, which is like, I think I should express this in terms of a gradient of its potential, and let the potential be of this form, some amplitude exponential minus I omega t minus k dot r, or for the sake of simplicity let me choose this in the z direction. So, k z. So, I want to find out that in the presence of this wave what is the modification in the electron density and what is the modification in plasma electron density, what is the modification in the beam drift velocity and plasma drift velocity. So, first of all I will write down the equation for the beam. So, let me calculate the beam response. The equation of motion is m delta v by delta t plus v dot del v is equal to minus E which is E grad phi. There is no magnetic field, I am ignoring the pressure term and collision term. This is the beam response is governed by this equation. Please understand, phi is the potential of the electrostatic wave, which is a small quantity. and V is the response. So, I can write down V as the original velocity of the beam. Actually, this equation has been written for beam. So, I will use a subscript B to designate the beam quantity. So, beam velocity is equal to original beam velocity plus a change in beam velocity due to the wave. But this change is very small because it is caused by a small perturbation phi. So, any product of V1b with V1b will be ignored, and whenever we solve the equation of continuity, the density will be also expanded like this: original density plus some perturbed beam density due to the wave. Substitute this in this equation. So, when I differentiate delta V0 b with time, this is 0 because this has no time dependence. So, this derivative goes away, only this term will survive, and when I substitute these two terms in here, I get 4 terms. But please remember, V0b does not depend on position. So, when you simplify these 4 terms, only one term survives because product of V1b with V1b is ignored. So, this equation, and I will divide this by m, takes the following form: delta delta t of V1b plus V0b, which is the z direction. So, only derivative with respect to z is to be retained, and V1b is equal to E grad phi upon m. So, this is the equation of motion after linearization. In the quasi steady state, response should have the same time and z dependence as the source. So, I will replace delta delta t by minus I omega, delta delta z by I k, and this equation gives V1b is equal to minus E k phi upon m. This is z component, let me write this like this, upon m, and here you will get omega minus k V0b. You may appreciate the effectiveness of Cherenkov resonance condition, that whenever omega is close to k V0b, this becomes nearly 0 and this becomes huge. So, that is the advantage of having Cherenkov resonance condition, that the response of electrons to a very small perturbation of the plasma wave will be huge if this condition is satisfied. Now, you can solve the equation of continuity, which is delta n1 for the beam, delta delta t plus divergence of, there are many terms, density into velocity product. So, this is n0 b plus n1 b into V0 b plus V1 b. This is the equation of continuity I have written. Please remember, n0b and V0b product does not depend on position. So, this will be 0. n0b into V1b certainly will be finite, n1b with V0b will be finite, but n1b and V1b product is too small. So, we will ignore it. So, then this equation becomes delta n1b delta t plus, this has only z variation. So, just let me write down delta delta z of n0b into V1bz, and this term plus n1b V0b is equal to 0. Replace delta delta t by minus I omega, and delta delta z by I k, you will get N0B V1B z plus N1B V0B. These two terms contain N1B, they combine together, and you can simplify this. You will get N1B is equal to K V1B z component into N0 divided by omega minus K V0B. Again the same denominator it was here comes in there, and that gives rise to a resonant enhancement in density perturbation. So let me write down N1B explicitly in terms of phi by using this equation, and the result is that the beam density perturbation due to the wave is N1B is equal to minus E k square phi upon m omega minus kz or kv0b whole square, and there is N0 also there, N0b. This is a important expression which shows that the density perturbation is scales as a square of this resonance denominator. It depends on mass also inversely. For ions, if I had written, this will be too small and you can ignore it. So I have got the density perturbation due to the of beam electrons due to the wave. For the plasma electrons, the difference between the two is that beam density has to be replaced by electron density of the plasma, and beam velocity to be taken 0 for plasma response. So plasma electrons response simply the perturbation in plasma density would be minus N0 of the plasma E k square phi upon m omega square, and ion density perturbation I take to be 0 because ion mass is too heavy. So if I know the density perturbations of all the three species, I can solve the Poisson equation. So the Poisson equation is del square phi is equal to E upon epsilon 0 into electron density plus beam electron density minus ion density. In equilibrium, all these sum to 0, but in case of perturbations this will be E upon epsilon 0 plasma electron density perturbation plus N1B del square I replace by minus k square phi, use this N1 and N1B in terms of phi, then this equation takes the simple form 1 minus omega p square, 1 is equal to omega p square by omega square plus omega pb square upon omega minus k v0b whole square, where I have used two symbols omega p and omega pb, which I am going to define in a little while. This is called beam plasma frequency. It depends on beam density. Omega p is the plasma frequency of electrons of the plasma, called electron plasma frequency. This has a term which is called resonant denominator. Even though the value of omega Pb is tiny, I think it will be better I should write this omega Pb here. Beam plasma frequency is defined as beam density in equilibrium E square upon mass of the electron into epsilon 0 to the power half, which is of the order of 50 under root of beam density. In beam plasma systems, beam density is much smaller than the electron density of the plasma, but because of this resonance, this term could be comparable to this term. That is the beauty. So, Cherenkov resonance is an important thing in bringing the response of beam electrons to be comparable to the contribution made by the plasma electrons. And not only that, this has in it built in this relation a possibility of omega being complex. Please see, this is a fourth order equation in omega, and it may have a complex root with positive imaginary part, and that is called the instability. So, I would like to simply solve this equation. There are two cases in which this equation has been solved and studied in great depth. One when omega Pb is small, and other case when omega Pb is the same as omega P. That is a very special case. People have studied that, but the most common case is the one in which beam density is small as compared to plasma density, and hence this term is small. Numerator here is smaller than the numerator here. Let us see. So, I will consider today the case when omega Pb is small, and I would like to solve this equation. I can rewrite this dispersion relation as 1 minus omega P square upon omega square, means I have taken the plasma term, plasma electron term to the left, and beam term I will keep on the right. Omega minus k V0b whole square. I can take LCM here and rewrite this equation as omega square minus omega P square into omega minus k V0b square is equal to omega square into omega Pb square. Well, this equation is fourth order in omega, and it is very difficult to solve for arbitrary values of k. For a special value of k, its solution is simple, and first of all I would like to find out that the case for which this equation is solvable analytically, that is also the case of largest growth rate. Let us see how. Please note one thing in here. I can rewrite this equation by dividing both sides by this factor. So, what do I get? Omega minus k V0b, then I get is equal to omega Pb into under root of omega square minus omega P square. Means what I have done, I have divided this equation by this factor and take the square root. So, I get this sort of expression. This says that omega is equal to k V0b plus additional term. So, omega becomes is equal to k V0b plus omega Pb upon under root of omega square minus omega P square. So, when omega Pb is small, this term will be small, and omega is nearly equal to k V0b. However, near omega equal to omega P, you expect that this contribution will be huge, and if omega is close to omega P but slightly less than omega P, this will be imaginary. So, you expect a very large growth rate when omega is close to omega P, but because I am presuming this term to be small, so omega is also close to k V0b. means when omega is close to k V0b and it is also close to omega p, you expect a large growth rate. So, what I am going to do, I am going to solve this equation in the special case when omega p is equal to k V0b, because in that case whenever this factor is small, this is also very small, and hence the right hand side, though very small, will make a significant contribution or modification in these roots. So, driven by this logic, I am going to solve this equation in a special case when k V0b is equal to omega p. It is a general technique of solving a complicated dispersion relation in plasma physics, that please look at the roots, the zeros, like here one zero is that omega equal to omega p, second zero is that omega equal to k V0b. So, we are looking for the simultaneous possibility that this is nearly 0, this is also nearly 0. So, that a tiny term on the right hand side makes a significant contribution, because this is the only source that can bring instability. If this term is not there, if this term is not there, the root of this equation is simply real. So, the instability is expected to come from the beam, though the density of the beam is small, we are considering, but still it could have a significant influence over the wave if these two are 0 simultaneously. So, we solve this equation for omega p is equal to k V0b. Then we say that omega is equal to, say, omega p plus some delta, which is also equal to k V0b plus delta. Use this in that dispersion relation and assume that delta is small as compared to omega p, so that higher powers of delta can be ignored. When you use this in that expression, the first term omega square minus omega p square gives twice omega p delta. The second term is omega minus k V0b whole square, which gives you delta square again. The right hand side is omega square omega p v square. So, here you get delta cube is equal to omega p v square, and this omega I will put nearly equal to omega p. So, omega p upon 2. Now, this is a cubic equation in delta. I should have 3 roots. To find 3 roots of this, I multiply by this quantity by a quantity called I L into 2 pi, because for any integer the value of this quantity is unity. So, you can always multiply this quantity by this sort of factor. So, delta turns out to be equal to omega p b square into omega p upon 2 to the power 1/3 into exponential of I L 2 pi by 3. Take 1/3 of this, or cube root of this quantity. This I can write as cos of L 2 pi by 3 plus I sin L 2 pi by 3, where L is 1 to 3, 0, 1, 2, 3, 4, 5, etc. But you will note that for L equal to 3, this will have the same value as for L equal to 0. So, the 3 independent roots are L equal to 0, 1 and 2, others are then repeated. Now, let me simplify this expression, means write down this expression in terms of cos and sin. So, delta is equal to omega p b square omega p by 2 to the power 1/3 cos L into 2 pi by 3 plus I sin L 2 pi by 3. For L equal to 0, this has no imaginary part. but for L equal to 1 this has the imaginary part. Please remember your frequency is omega p plus delta. I am looking for a solution where omega has a positive imaginary part, so that the wave amplitude grows with time. So, I am looking for delta to be positive imaginary. So, for L is equal to 1, delta has positive imaginary part, and hence the frequency will be complex with a positive imaginary part. And imaginary part of omega is the same thing as imaginary part of delta, is called the growth rate. Growth rate is called gamma, which is imaginary part of omega, which is the imaginary part of delta, and if you calculate from here, put L is equal to 1 in these expressions, imaginary part will give you root 3 by 2 and becomes root 3 by 2 into omega p b square into omega p by 2 to the power 1/3. So, growth rate, and how will the amplitude vary? Electric field of the wave, which is Z A e to the power gamma t into e to the power minus I, real part of omega into t minus kz, this is the field. So, this is the amplitude of the wave now, it is growing with time, and growth rate is scales with beam density and electron density, it increases with both of them, and this is a very important result. So, we have seen that if the beam velocity is very close to omega p, then the phase velocity of the plasma wave, in that case the beam can give energy to the wave. Further implications of this we will discuss in our next lecture. Thank you very much.